Спасибо. Доброе утро, друзья. Good morning. I hope everyone had a good time at the party last night. It was pretty amazing. It's my first time seeing Sam do that live show, and it was really, really incredible. So hopefully we have something entertaining again for you this morning to kick off the second day of JokerConf. We're going to go on a journey, you and I. We're going to journey into the wonderland that is the JVM and explore some things you may never have seen before happening below, all the interesting and strange things that the JVM does. So first, a bit about me. Charles Nutter. I've been a Java developer since pretty much the beginning, 1995, 96 or so. Right now I'm working at Red Hat. I work full-time, although some of my time is spent on other things, full-time on the JRuby project, which is a Ruby running on top of the JVM. It's just like regular Ruby, except you can call Java libraries, you get the benefits of the Java platform. I also have spent a lot of time digging around, hacking on, exploring the internals of the JVM. In order to make JRuby a good runtime, a good Ruby implementation, we had to do a lot of digging and understand how the JVM optimizes. And hopefully what I've learned over the years will help you do some similar sort of work and be able to understand the JVM. So, as I said, we're going to go on a journey here, and I think it's useful to talk a little bit about my journey and how I came here. Like I said, I started doing Java in about 1996. I got a university job doing essentially web development, long before Java was even appropriate for doing web development, long before servlets, long before XML, all those sorts of things. And my career progressed, as I'm sure some of you have done. I made it all the way to the top. I became a Java enterprise architect, the most exciting title in the software industry, I'm sure. But while I was in that role, I was introduced to the Ruby language. And so in about 2005, I went to my first RubyConf, and I was so struck by the beauty and the simplicity of the language that I wanted to try and make a Ruby on top of the JVM. It turned out that JRuby already existed, but it needed a lot of work. It needed a lot of help. And so from 2006 until now, working for Sun Microsystems, Engineered, a Rails company, and now Red Hat, I've been trying to make JRuby the best Ruby implementation in the world, as the best possible, and ideally the best one. And during that time, I learned a lot about how the JVM works, and I want to be able to explain all of that to you. So today, what we're going to do is explore what the JVM does with Java code that you feed it, both at the bytecode level and even at the native level. And we're going to walk through a few specific Java features and what they actually look like running on the JVM. All right. So, like I say, some interesting Java features that you're all used to and that you're all using in your daily development. We'll see how they're compiled down to bytecode, which in some cases can be a little bit surprising, what actually comes out in bytecode. We'll see what the JVM does with that bytecode and how it optimizes code. And then we'll actually look at the native code that's generated and walk through it step by step. So the first obvious question here is why would we want to do this? You don't really need to know what the bytecode looks like. You don't need to know what the native code looks like. You just write your Java code, you throw it onto a JVM or into an app server, and it does what it's supposed to do, right? Well, let's think about who you are. So I assume a lot of you are Java programmers, Java developers. Many of you may be focused on performance, analyzing an application, finding bottlenecks, looking for things to improve. We all have to do debugging at various times. And in general, all of us have done these roles at some point. Maybe these aren't our primary roles, but we have to do them on at least occasionally. And it turns out that the details of how all these things work really does matter. The details matter. These cool features that we have, lots of them in Java, some of them in Scala or Clojure or JRuby, they have a cost that you can't see normally. For example, inner classes, before we had lambdas, constructing a new object every time was very costly. So you do that in a very hot loop, you lose performance. But you'd never realize that by looking at it. Structural types in Scala, which currently I believe still use reflection all the time. Very simple looking feature, just a few characters in your code, but a massive overhead behind the scenes. And of course, the devil of serialization that we have to deal with, and how it performs, how it doesn't perform. These are all features that seem obvious and simple at first, but they have hidden costs that we need to explore. And so today, hopefully, we're going to explore how the code design, the features that we use and that we love in these languages do have a cost, they do impact performance, and a little bit about what the JVM can and cannot do for you. Okay, so starting off, we'll talk about this idea of the sufficiently smart compiler. You may have heard this in other forms, but the idea is that if you take a good enough compiler, if you can make the compiler smart enough, you can make your language have any number of features, high-level abstractions, and it will still manage to compile it down. And this is kind of a myth. Like, you can never get all the way to the sufficiently smart compiler that makes high-level abstractions completely melt away and optimize the way low-level code would. And in terms of the JVM, this is the idea that if you wait long enough for some definition of long, the JVM will eventually optimize everything perfectly. And even your awfulest code, your even most horrible code, will run well. And of course, we know that's not true. And for some definition of long, maybe in 1,000 years that code might run and to get enough information about it, and another compiler will come in and do it. But there's always going to be performance gaps when you have a higher level abstraction on top of a low one. So before we dive into this, any good journey needs a map, and so I'll have a little primer on some terminology, how the JVM works internally, before we get into the nuts and bolts here. So most of these terms will be familiar to you folks. So the source code is obviously the Java source that we write, or Scala, or Ruby, or Clojure, or Groovy. That gets compiled into bytecode. The bytecode is basically just a binary form of that program that represents all of the flow control and all of the actions it does, and the JVMs all can run this. It's a standard across all the JVMs. Once we've run that bytecode long enough, ideally, we want to turn it into native code so that the CPU is actually running it directly, rather than running through an interpreter with all the overhead that goes along with that. The heap is the JVM-controlled area of memory where all the Java objects live. This is the managed space. So all the objects that you have that are garbage collected go onto the heap. JIT, or just-in-time compilation. This is a sort of a lazy way of turning one program form into another. In the case of JRuby, it turns our JRuby interpreted form into JVM bytecode lazily as necessary. In terms of the JVM will take that bytecode and at some point in the future turn it into native code, and ideally do some optimizations along the way. That's opposed to ahead-of-time compilation, AOT. This is compilation that happens before runtime. So in a sense, Java-C is an AOT stage because you don't run source directly on the JVM, you run bytecode, so you compile that ahead of time. If you're familiar with CLR or the .NET platform also does AOT. The first time you run your application, it goes through it and statically analyzes it, dumps out some native code, and then from then on it will use that code. But it will actually do this before it ever runs. So if we look at how the JVM works, we've got our Java-C at the top. We turn our Java source into JVM bytecode. This is obviously familiar to anybody in the room that's done Java development. And for a lot of folks, this is as far as you need to go to understand your program. You take Java source, you compile it to bytecode, and magic happens. The application works. Now inside the JVM, the Java bytecode, the JVM bytecode, runs inside a bytecode interpreter of some type. And that essentially just walks down the bytecodes, does what they say. Load this field, make this call, set this local variable, and then it loops over all of the bytecodes that you've fed it. Now, as it does that, it gathers information about what the program looks like. Perhaps there's a branch that you never follow. Perhaps there's a lock that is never contended or is unnecessary. Perhaps there's an object that you create only for a brief time before walking away from it. The JVM can turn that information into optimizations, eliminating objects, coarsening locks, and then it takes that information, turns it into native code that ideally is optimized for the way it actually runs. And this is a big distinction with JIT versus AOT. An AOT compiler, an ahead-of-time compiler, can only analyze what it sees in the code. It doesn't know what the actual flow of the application will be, which is why a JIT can often produce better code than a static compiler, like a C or a Rust compiler, for example. So some of the optimizations that the JVM does, a lot of the optimizations the JVM does depend on what's called inlining. So inlining is where if you keep calling the same method at the same point in your code, well, let's just stick those together as one piece of code. Optimize the whole thing. Rather than constantly jumping from one side to the other, constantly doing this call of some function out in memory, let's turn it into one big function and optimize the whole thing. And then what is optimization? Well, optimization, put simply, is doing the least amount of work to accomplish some goal. And so a poorly optimized application or a runtime that doesn't optimize well is wasting time to get the same amount of work done. And what we're always trying to do as far as performance on our platforms is do the least amount of work, get to the finished product very quickly. So let's look at how inlining works here for an instance method. So we are going to make a call to some method on a target object. We've got our arguments and we've got our target. So we load the target and the arguments. We check if we've cached this method before. We've already looked it up. We know about it. If it's exactly the same as it was last time, we can just start executing the body of that method without branching, without doing a separate call. But there are guards in place. There are checks. So if it turns out that we've now got a new object with a new method, well, now we need to go back and do an actual call and figure out what that new method is. Possibly re-optimize, inline something differently. Inlining a static method or a special method, and special methods are, for example, constructors. In those cases, it's basically a function in memory. There's only ever going to be one system.get property, for example. Much easier for it to optimize. We don't need to do as many checks, so we can just usually start running that code directly. We load the arguments, call the function, and we're off and going. So we've got a few tools that you're going to see used here. Java-C, obviously everyone's familiar with that. Java-P, which is another fun tool. Who's played with Java-P? Okay, that's a surprising amount of hands. Java-P is basically a Java disassembler. You can dump out the actual bytecode of a given class file and see how it works internally. And then some JVM flags. These are specific to Hotspot, the OpenJDK JVM. Print compilation, which will print out a log every time a method is compiled down to native code. Print inlining, which will display a tree of how the methods have been inlined into each other, or why they weren't inlined into each other in some cases. And then my favorite flag, print assembly, where you can actually look at the native code that the JVM is outputting when it does these compilation and inlining phases. Okay, so now we have our primer. We're on the same page for this. So let's go down. We'll now go down, follow the rabbit down the rabbit hole. And we'll start with something very simple. We'll start where all good programming talks begin, with a hello world here. So here is our hello world. Still, I believe, the longest hello world in the programming language universe. We've got our main, we've got our class, we've got our hello world printing out. So let's start level 1 and look at what the bytecode for this actually looks like, okay? So we take our Java-P, and if we just run it directly with no additional flags, specify the jar, the class path, and the class we want to look at, we just get sort of an outline view of the class. We can see the methods that are there, we can see the names, we can see the return values and the argument types, but that's about it. Not very interesting for our talk, so we'll continue on here. If we add the -c flag, well, now we get something more interesting. Now we get the main method, and we get that same outline structure, but we can see the bytecode that's actually being run when we run this program. And this is where we will start to dig down a bit more. So here we have our first bytecodes that we've seen in the talk. So get static and put static, you'll see static field accesses. So this is system.out, accessing a static field on a class somewhere in memory. LDC, which you'll see in a lot of this code, is just to load some constant value. And constant values, as far as the JVM is concerned, are numeric values, booleans, strings, and then method handles also have constants. And there's a few other internal types that are not important for this talk. We have invoke virtual. This is the call to print stream print line on system.out. This is just calling an instance method. There's also invoke static, invoke special, invoke interface that do what you'd expect them to do. And then return, of course. Just a plain return is a void return, not returning any value. There are return types for all of those primitive values and for a reference type as well. All right, so back to our bytecode here. And now we can kind of understand what's happening. So we can walk through the code and basically see exactly what we'd expect to come out of the Java compiler. We get system.out as a static field. We load the constant string, hello world. We invoke the method printstream println with that hello world, and then we return from main, and our program's done. Not too bad. I think we can all understand that. So let's go another level deeper now. Now we're going to actually look and see what the JVM does when it decides to compile and optimize this code. So we'll be using the print compilation and print inlining flags. So we can see the methods when they compile and see what inlining decisions the JVM has made. Okay, so the hotspot JIT is what we're talking about here, but most of the JVM JITs work in a fairly similar way. So this is generally applicable to any other JVMs, and most JITting runtimes too. So as we showed earlier, code is interpreted first. After some threshold, which can be a number of times the method was called, a number of times a loop has iterated, the JIT will start running. The JIT will take that code and turn it into native executable code. Now, anybody who's doing Java for more than maybe 5 years or so remembers a time when we had this clear distinction between the client compiler, the client JIT, and the server compiler. And the client compiler was the one that started up quickly, didn't do as much optimization, but it didn't take as long to get going. So it was good for startup time. And the server compiler, what's called C2, was the one that actually analyzed that code, let it run longer, did more profile analysis, gathered more information. It took longer to get up and going, longer to start, longer to warm up, but the ultimate result was much faster. And we kind of had to choose which one of these. A lot of us would use client in our development environments, and then flip over to server when we went and deployed to production. These days, they've kind of been merged together in Hotspot in what's called the tiered compiler system. So now, rather than going all the way to client and staying there, or going all the way to server and staying there, there are a few different grades of compilation in the middle. So usually what will happen then is the code will interpret for a while, then it will go to a sort of client plus, let's keep gathering some information. So it's like the old client compiler, but it's still analyzing the code, still thinking about it. And then it will, again, be able to take that information and go to the server compiler, the more optimized compiler. So ideally, we get faster startup, and we don't have to give up straight-line performance. We can get fast startup, reasonable warm-up, and good long-term performance for it. Now, for the purposes of this talk, we don't need to deal with all the different stages of the compiler, so we will be disabling tiered compilation and essentially just doing the full-on optimization, the server compile. Okay, so here's our hello world. We're going to write a little program that loops over it so that we can force the JVM to compile it. If you just run hello world directly, none of that code you've written will generally even go to native code. It'll just be interpreted once and then thrown away as the JVM dies. So we'll loop a few times to get this to JIT. A bunch of flags here. So -x batch basically does all of the compilation. When Hotspot decides to compile this down to native code, it will do it in serial with the program execution. It'll do it all at once. So you don't have interleaved log files. You don't have multiple compiler threads fighting for printing out logs. There is the tiered compilation disabled. And then we'll just look at print compilation right now. And then I piped some error stuff to dev null just because it's mostly just visual noise. And what we get is an output like this. So this is the output actually from the Hotspot JIT showing the methods as they're compiled. And if we look over the different columns here, the first column is how many milliseconds have passed since the JVM started up. The second column is what index of the compile is it. It's the first compile, or the second compile, or the third method that's compiled. The bang, the exclamation point here, indicates that the method has try-catch logic, exception handling logic. And so there's special things the JVM needs to do internally that are slightly different than a method with no exception handling. The percent down at the bottom means that it replaced this method on the stack while it was running. So you've got a method that loops, it never gets called more than once. The JVM will still see that and think, okay, that's running a long time. I think I'm just going to compile it and switch to the native version while it's executing. It's kind of a magical thing that it's able to do. And then, of course, we've got the classes, we've got the methods, and the actual size of the method in, I believe this is bytes of bytecode. And it uses that to determine, oh, a method might be too big to compile, or a very small method, maybe we inline that right away. And so this gives you a general idea of what's compiling. And so as far as our example goes, here's the code that we actually wrote, our hello method, which is very small, just 9 bytes of bytecode, and our main method, which is 18 bytes, a bit larger for that looping that we do to make the JIT fire. And now we can look at this log, and what have we learned? We've learned that our code is actually compiling. It is actually JITting at the JVM level, so we're doing good. We actually should get some of the performance that we hope out of this. So now let's add in a little bit more information. We're going to use the print inlining flag, which is considered a diagnostic option for the VM. So we have to enable diagnostic options. I find it strange that we have to do this, because if you omit that flag, the JVM will say, you should have passed unlock diagnostic VM options. And I could just say, why don't you do that for me, JVM? But as it is, we have to turn on these options, and then we can see the inlining. Now the output gets a little bit more unusual here. We can still see our methods are in here, and we can see our hello and our main. But we can also see that hello was inlined into main. We can see that the print line logic is being inlined into each other, and kind of get a tree of these things. We'll come back to some of this output a little bit later, so you can see some of that. So now we know we've got code compiling at the JVM level. We've got code inlining into each other. Let's go to the next level. Now we're actually going to use the print assembly flag. This one is not supported out of the box on a typical OpenJDK or Oracle JDK build. If you Google for hotspot print assembly, there are binary, a library, a DLL basically, that you can drop into your JVM installation, and then print assembly will work. So are we all excited to go to this level? How many people have done any work with assembly code? Okay. A few of you. The hands are there's fewer hands every time now. But nothing to fear, this is going to be a lot of fun. All right, here's our command line now. We're not going to do anything with the compilation logs anymore. We just want to see the assembly output. Again, a diagnostic option, so we have to turn it on. And then we run our program. And here we are. Now we actually have assembly output. And this is what the JVM produces for this code. However, this simple example, what we would consider to be the simplest programming example, is actually incredibly complex. There's a lot of string manipulation that's going on. There's I/O that's happening. And if you just ran this with a hello world, you get thousands and thousands of lines of assembly for it. We're talking about print line inlining. We're talking about the accesses of system.out in there. Too much for us to look at. So let's take an even simpler example here. Yes, so these are the numbers here. Too much stuff. 2,700 bytes of assembly that came out of this particular program. The client compiler, which doesn't do as much inlining, is still 600 bytes of assembly. It's still a lot of code to read through. And of course, most of this output is because lots of methods get inlined together, lots of stuff is optimized together, so a long assembly trace. So we'll take a step back here. So let's do something even simpler. We're just going to loop over a simple method. That method just adds 1 plus 1. Much simpler. Not doing a lot of printing, not doing string manipulation. And so it's interesting to look first. Let's see what tiny looks like at a bytecode level. What do you think? You'll notice that it's actually just loading 2 onto the stack. Now the JVM, traditionally, we haven't really thought about Java-C doing optimizations for us. It doesn't really do a great deal of them. There's a few things that it does. This is one of them. If it looks like it's a constant expression, 1 plus 1 is always going to be 2, there's no reason to actually do load 1, add them. So it'll just load 2 and then return it. Other optimizations that it will do is inlining final constants, for example, final strings. We'll see a little bit of that later on, too. So if we look at our compilation log here, we've got our tiny method that compiles. We have our main method that compiles with tiny inlined into it, which is because it was hot. It was obviously being called a lot. And now we can look at the assembly code. So here's the assembly code for tiny. And a lot of this is just kind of visual noise dealing with native stacks. But here is our move with value 2 into the EAX register and our return. And there it is. Very simple. In this case, we don't use the result of tiny, but the method itself doesn't know that. All it's got to do is return 2. And so there's the code that does that. Pretty simple, similar to the bytecode. Now, if we look at main, now we have much more visual noise. I wouldn't expect anyone to just be able to read through this the first time and understand what's going on. So let's try to pare this down a little bit. So first of all, we can remove some of the additional comment output that the JVM helpfully provides to show you where in the program this piece of assembly is executing. And now we've got to boil down to just the basic instructions that are actually emitted for this. You'll notice there's a move here in EAX dealing with RSP, there's a push of RBP, there's some subtracts information, and then on the other end an add and a pop. Well, on the native level, when a Java method executes, it has to have a place to keep local variables. Sometimes those will go into registers, sometimes they will be on some execution stack. Similar to how you push a value down on the JVM stack, that's how the native code works as well. You need to store it somewhere. And so there's a long area of memory that has all of the local variables for all of your active Java methods. And that's not interesting for purposes of discussion here, so we'll just omit that. OK, so we're getting boiled down a little bit more. The next stuff you might see here is this unusual test instruction. Well, these are safe points in the JVM. A safe point is basically the code is executing, but it needs to check in periodically with the rest of the JVM. Maybe garbage collection needs to run. Maybe new code was loaded, and this is no longer valid to continue executing. So here we have our safe points that are basically just asking the JVM if it wants to jump in and change the world a little bit. Again, for purposes of our discussion, not important. We can peel that out. So now we're getting boiled down a little bit better here. There's also this unusual one. So we're exchanging the register with itself. What do you think that is? Some people know. This is basically just a no-op. And actually, in x86 assembly, a no-op and this instruction are the same mnemonic, the same value. So this is doing nothing. Why do we have an instruction that does nothing? Well, the JVM likes to execute some of these instructions on a particular boundary. In an older system, a 16-bit boundary, or 32, and now a 64-bit boundary. So we ideally want the next instruction to execute at that same sort of boundary. The native processor does a better job of dealing with it. So we have our no-op to just kind of pad things out. OK, so we'll peel that out of there. Again, not interesting for our discussion today. And then we'll pare down these addresses that make a lot of noise, make it a little more difficult to read. And this is essentially what we have for our program. So now we can actually follow this through and read it line by line and trace it all the way back to our program. So let's do that. First of all, we're going to initialize I to 0. And in this case, I is being stored in the ESI register. So we move 0 into ESI. Now we have a jump. So we'll jump down to 4. At instruction 4, we're doing a comparison of ESI, our I variable, our index variable, with 1 million. OK, is it actually 1 million? And I notice a little typo there. We're actually comparing it. This is the comparison in the for loop to see if we've incremented beyond that maximum. In this case, let's say we haven't. We're going to continue with the loop. Now we've got to jump back up to 3. Instruction 3 increments ESI. That's the I++. And then it loops that way. It loops that way until we actually get to a value that is larger than or equal to our final value, our final condition. And then we have our return. And then we exit the method. Very simple. And now, the astute observer might notice that this loop doesn't actually do anything useful. And if you let the JVM chew on this for a while and hand it off to the C2 compiler and let it make some decisions about optimizing, what you'll actually get is this. It'll actually optimize the entire loop away because it doesn't do anything. And this is where it really starts to get interesting. Now you can see how a runtime optimizing system, a JIT system, can do a better job than static analysis. You can determine that there's no useful work being done here, and you can eliminate all of it. And so our program that does nothing now literally does nothing. So the point I want to get across is that it's really not that hard to understand even the lowest levels, even the assembly that's output from the JVM, if you know where to look, and if you can kind of squint and get rid of some of that additional noise. So, part 3, this will be the interesting bit. Now we'll actually start looking at some Java features that we're used to using and see what they actually do at the JVM level. Okay, so these are the features that we're going to look at today. We're going to look at how final fields are dealt with by the JVM's JIT, how it optimizes around them or does not. We'll look at synchronization and some concurrency primitives and how those optimize. We'll look at the string switch that was introduced in Java 7 and show how that actually executes in the JVM. And then we'll talk a little bit about lambdas as well. Okay, final fields. So a final field is just a field that can't be modified, and we put can't in quotes because on the JVM you can always cheat, but generally can't be modified. And based on that assertion, the compiler can do optimizations. It can improve the code. If it knows this value is never going to be replaced, maybe it just puts it directly in. So let's take a look. So here we have a simple method, a simple little class here with two strings, static final strings. One of them is initialized directly with a constant value in the code, and the other one is initialized at boot time, at runtime, by looking up some property, calling some function. But once they're both assigned, once they've been loaded, they shouldn't change ever again. And then we'll print those both out. So the first interesting thing is to take a look at the bytecode level. And many of you may have run into this. You have a constant in your application somewhere that's a static final string. You change that string, recompile your application, and it doesn't change. In the application, it doesn't actually modify other classes. Well, the reason for this is that when you have a static final string directly initialized in the code, Java-C actually will just use that string as a constant everywhere. It actually inlines it on its own. So this is long before we're even at runtime. For the other one, the property lookup, you can see that it's actually going to go and get static. It has to look up that property each time. Because it doesn't know what it is when Java-C compiles, it needs to look it up at runtime. Okay? So let's make this a little bit more interesting. We'll take these two strings and add their hash codes together. Let's see what we actually get out of this. Now, we'll go down to the assembly level. At the assembly level, for the directly initialized string, we see what we would expect. It just loads the address of that string because it knows exactly which string it is, and it accesses the hash code field. It calculates the hash code and gives us the result. Okay? What's surprising here is that the lazily initialized static final string does exactly the same thing. It has the string, it knows it's there in memory, it's seen it executing with this same string, this same final field, and so it can actually just go directly at that string without having to go load the field every time. But it doesn't see through all the way. It's actually trying to go in and get that hash field. It's not just loading the value that it knows is the appropriate hash code. So here we've got a little, we found a little bit something about the JVM, and it does it a little bit differently, the optimization. Let's look at another example. So this is now final strings, but not static final strings. We're going to add the hashes for those two. So all we've done is remove the static from these fields. We'll take a look at the bytecode. Okay. Well, we don't see any of the constants. We only see the first constant again. So add hashes, load constant. This is an instance string. So it knows that that field is always initialized to the same value. It can inline the string directly into the code. The other one does have to go and get the field every time. So similar to what we saw with the static finals. Now, if we look at the assembly code, here is the instance, the directly initialized string. Okay, we load that string out of memory. We have our inlined hash code logic, and then we can see the hash code, similar to what we had in the static final case. Well, let's look at the other one here. So now we have our get field. This is the lazily initialized value. We have our add hashes, and it's not doing quite the same optimizations here. It's not doing the same optimizations even though that value is still constant. It is still final. It doesn't optimize the same way as the other one. So here we go, is our first achievement. We found something that Hotspot could do better. And actually, before Java 7, static final fields that were lazily initialized did not optimize at all. They actually did look up the field every time and go find it in memory and go grab that field. So that's something that's improved. And this is the story of the JVM. This is why you get that free performance boost every time you upgrade. Little bits and pieces that come in over time for optimizing this code. Okay, concurrency stuff. Let's take a look at this. So we're going to look at synchronized, what that actually does at a bytecode and at a native level, and then what volatile does. So here's our little concurrency class. And for this case, all we're going to do is system current time millis. And in the one case, we'll call it as a normal method, no synchronization, no locking around it. The other one will have a lock. We need to lock around this, make sure that no one calls this current time millis at the same time. So here's the bytecode that we get. So we don't see any synchronization on the call side. These both look like they're just static method calls. We call getTime, and we call our getTime synchronized. Not too surprising here. If we look at those methods, we also, it's still a little bit surprising. getTime and getTime synchronized still have the same code in the body of the method. This is something that Java-C does kind of magic for you. When the code loads, it sees that it was marked with a synchronized bit. And so the JVM will treat this as if it had a synchronize on this object or this class wrapped around the body of that code. But Java-C doesn't actually emit that into your bytecode. It's just a flag. Always synchronize around this method. Okay, so let's go down to the next level. So here's our simple getTime. We move the system class into a place where we can access it, and we call a method on it, current time millis. Simple enough. Now, what does the synchronized version look like? Well, it's significantly larger. And this isn't even all of it here. So what we've got essentially the same logic at the bottom. This is move system somewhere I can access it, access the system class, call the current time millis function on it. All of this other stuff is the synchronization overhead. And we've got moves in and out of memory, lots of register stuff. We've got various values that we're trying to set. And what this is essentially doing is it's taking the system class and setting a bit on it, setting some bits that says, okay, this is a synchronized now. We're synchronized in this case. I've got the lock that goes along with this class. So no one else can have it. But it has to check, did I lock it already? Does somebody else have the lock? Do I need to wait for it? And so you've got this code at the top, but you've also got some branching that has to do other logic here. So we'll talk about a little vocabulary here. So two optimizations that the JVM can do with locks. It can coarsen them. In that case, it sees that you're relocking the same object repeatedly. Maybe it'll just lock it once, do all that work, and then unlock it. So we can avoid all that extra overhead of the locking in a tight loop. Locky lighting is when it turns out that the lock is not necessary at all. So for example, you create an object, you synchronize on it, do something with the object, and then throw it away. No other thread sees that object. There's no reason to have the synchronized logic around it. The JVM can see that and can eliminate the locks in those cases. So a lot of the code that you see being emitted for a synchronized section or a synchronized method is to do one of these two things. So we'll go back here, and I will notice that we've got some moves, we've got some stuff up at the top here. You can see the move at the very top. It says, okay, that's a Java-lang class object. That's essentially synchronizing on the system class. So we come in here and we're like, okay, well, let's jump down. What is this? What's at this address? If we go down to that address, that's where we actually see the lock. So if it turns out that we haven't locked this object, it will actually do a lock instruction at the native level. This is to make sure that only one thread can lock this object at the same time. And that's where we actually have our locking. And so this, when you see a lock like this in your assembly code, it means you are paying a cost. You are forcing the processor to do a bit more work than you would normally want it to do. And if you're doing this too much, this will end up costing you lots of performance. I'll show an example later where we found a bug in JRuby as a result of this. Okay, so let's take a look at Volatile.
So volatile is one of those concepts that some Java developers know well, but most it's kind of a fuzzy concept to them. So in various ways of putting this, but a volatile basically forces any changes that you're making to an object to be done in a certain order. So if you update a volatile field, the guarantee is that any accesses that happen in time after that modification, after you've changed it, will see the new value. And there's other rules that go along with this. But the important thing about this is that it does actually prevent certain optimizations. The JVM may reorder your code if it turns out that it's more efficient. The JVM may eliminate certain field accesses if they're not necessary. It can't do that for volatile. So it has a similar impact to locking. I knew you were going to be trouble back there, Alexei. And there are some cases where it can't do with the same optimizations that it would do with just a normal field access. And we'll see what that actually looks like in the JRuby code here. So I was actually looking at a performance problem that we had with JRuby. We had our Ruby basic object, which is our top-level object in the system. And I couldn't figure out, we had a serious regression on performance. For some reason, all benchmarks were significantly slower, much, much slower than they were in a few revisions ago, and it wasn't clear what actually happened. I had to get out the toolkit and dig down and start looking at the actual assembly that came out of this. And so I knew that having a lock instruction in here didn't make a lot of sense. This is just a constructor. Why do we have this volatile write happening all the time? Every object that we create is doing this volatile operation. Well, I went back to the code, and we have this growing variable table in every object in JRuby. Ruby objects don't declare their fields ahead of time. They're just kind of added to an object as it goes. And we need to be able to do that in a way that all threads see the updates at the same time. So our variable table, where we actually keep those values, needs to be volatile. Turns out this is not such a good idea. So we've got this object with a volatile field. Every time that object is created, we do a volatile write to it. And that's forcing a lot of things to happen at the CPU level. The issues that I've talked about earlier with the having to make that visible to all other applications, to have to order these to all other threads, to make these the order of these operations happen in the right order. This was actually costing us a tremendous amount of performance. Every object in the system, every number, a fixed num, every string, was doing this volatile write every time. So we modify this. Actually, just leave it null. Don't initialize it ourselves. Let it remain the default value at the JVM level. And there we go. Another achievement unlocked here. Managed to fix a Java performance bug that I would never have been able to investigate, never been able to see the actual problem unless I actually looked at the assembly code. It's very difficult to tell what's happening, because if every object has added all this overhead, the performance profile's all over the place. It's very difficult to see what's actually taking up all that time. So this was a nice one, too. We actually fixed it. I think the benchmarks went back to being where they were, about twice as fast. OK, let's look at a more recent feature here, string switch. It was introduced in Java 7. Everyone was very excited about it. I've used it a few times myself. But how does it really work under the covers? In order to do that, we need to take a step back and look at the switch statement itself and how that actually works. So we've got our switch. It has some numeric value come in most of the time. And then we have case values or case targets that are constants. And anybody who's done any Java programming has run into the Java C compiler saying, I can't do this because it's not constant. You can't go look up a field and have that be the target of a case, for example. So depending on what those values are, those case values, we can do a very fast version of this branching. We can just have a table, and we look it up at a particular index in that table, find where to branch to in the code, and go straight there. If it's a wide range of values, well, we have to do a little bit more magic to try and find the right target instruction to go to. So let's take a look at these at the actual bytecode level. So here we have a simple switch. We've got some number of arguments that are coming in. That's what we're going to use as our dynamic value, our variable value. And depending on how many arguments we have, we're going to print out 0, 1, or 2. If we look at this at the bytecode level, this becomes what's called a table switch. So table switch has a contiguous range of offsets. We've got our 0 value, we've got our 1 value, and we've got our 2 value. We just look into this table, find the next instruction we're supposed to execute, and branch right to it. Fairly simple. Let's look at a different case. So here we have a switch where the values are not contiguous. The switch isn't even in order. We have 2 million before we have 1 million and 3 million. What does this actually turn into? This is called a lookup switch. And now, the first thing you'll notice here is that the Java-C compiler actually did order these cases in this table. And that's because the lookup switch actually has to do a binary search. It will find an entry in that table to branch to by taking the value in hand, looking at the table. Is it in the middle? Nope, it's lower than that. How about here? How about there? And for any of you that done a computer science, that's an O of log n operation. So we're talking about going from a constant time, jump right to this instruction, to let's search around. We got to figure out what instruction to go to. And when you write your Java code, it's good to know about the difference between these two, because the performance difference between a table switch and a lookup switch might be important for your application. All right, so let's get to the point. Let's get back to switch here, or a string switch. So what kind of switch do we use for strings? You can think about that for a minute. A table doesn't work because hash codes are going to be all over the place. A hash code is going to be definitely not contiguous, probably lots of different values that are going to be in the table, so that doesn't work. Now, if we just do a lookup, well, we still have to make sure we've got the right string, because many strings will hash to the same value. And so the answer is, in the JVM bytecode, you actually use both and do an equals check. So let's take a look. We've got our string switch here. We'll go based on a couple different languages on the JVM. We've got Java, Scala, Clojure, Groovy, and Ruby. And then depending on which one, we will print out or return a particular string. So let's look at the bytecode now. Now we see our lookup switch, and those values on the left are the hash codes. The way that a string hash code is calculated in the JVM is part of the JVM specification. So it actually does get emitted directly into the code here, and it's guaranteed not to change. We know that JVM to JVM, these strings are always going to hash the same way. So we've got our lookup switch, but there's also this unusual, this hidden variable up here. We didn't have any little variable that needed to store a 2, or that needed to store a -1. The iconst m1 there is load a -1 constant onto the stack. iStore2 is put that value in local variable number 2 in the list of variables. There was no such variable in the code we originally wrote. In fact, if we look at this, the only variable that's coming in is the language. So why does it have a second local variable here that it's dealing with? Well, let's dig down a little bit deeper. Let's look at the Scala case. So we load our incoming value, our language string that we're trying to react to. We're going to check and see if that's actually the Scala string. And so this is where we do the equality check. We need to make sure that this isn't just another similar string that hashes to the same value. So we take a look at the string. We know what the hash code is. Now we know it actually is the Scala string. Now we store a 1 into that hidden variable. So we know that it's number 1. It's the first one here. If we continue on, there we go. Now we're actually using that variable. So this is our second switch. Now that we've determined, yes, this string actually is the Scala string, now we do our table switch. We take that index, that value that was hidden away, and we know what instruction to branch to. So in this case, it's Scala. That's value number 1 in this table. We branch to instruction number 167, instruction offset 167. There is our LDC of the Scala string that we want to return from the method. And you can see all the other ones are there too as part of the table. So interesting. We're hashing an object, we're checking for equality, and then we're doing whatever our result is. It actually works out to basically this code in Java. So here is our hidden value, target equals -1 to start. We haven't found a value yet. We've got our hash codes for each of these strings. We determine which of those strings it is and confirm it's actually the same string that has equality. Then we go to our second switch and do the actual work. So this is what the Java-C compiler produces under the covers. In order to add string switch, all that needed to change was Java-C. It wasn't something that needed to be changed at the JVM level. And if you've ever implemented a hash table, that's essentially what this is. is basically doing an inline hash table to look up the string, get a value that is our branch value, and then go to the instruction that's indicated by that. Interesting, huh? So we're not going to go down to the assembly level. I think it's pretty obvious this is just magic that happened at the Java C level. But let's look at something that's an even more recent feature, Lambdas, Lambda expressions. So new for Java 8, and again, everyone was very excited about it. Anybody who's used Lambdas has fallen in love with them, I'm pretty sure. The key goals here was that we wanted something that was lighter weight than inner classes. We didn't want to always be creating a new object every time. We didn't want to have a class dumped out onto the file system for every single Lambda. We dealt with that mess with inner classes. That ship has sailed. We don't want to have to do that again. So let's have no extra classes at the .class file level. And we wanted it to be really optimizable by the JVM. Wanted the JVM to be able to see through these things and optimize them. And in some cases, we've managed that. In other cases, maybe not as much. So we'll look at a Lambda thing. Here is our outer loop of this little Lambda demonstration. So we've got our list of languages. We're going to sort them. We will get the non-capitalized part of the string. We will get that string as an all-caps string. A few other things. We'll look at a couple of these. So here's our sort. So we've got our collections.sort. We've got our list. And then we have our closure that is basically just doing an integer compare of the two string lengths. So if a string is longer, it should come later. This is our doSort at the bytecode level. And you'll notice something new here. Now we actually have an invoke dynamic instruction here. So what is this doing? Why would it be doing a dynamic invocation? It's all statically compiled code. Well, the magic here is that the invoke dynamic lazily goes out and creates that Lambda class and object for you. It lazily creates it. So rather than having a .class that's emitted and dumped onto the file system, you do it at runtime, and only if you actually need it. So our invoke dynamic goes out and says, OK, I've never created this Lambda before. I don't know anything about this class. Let's create a little object to wrap around it. So let's take a look at the actual bytecode for some more of this stuff here. Now we have what's called a bootstrap method. So when the invoke dynamic is first executed, when it first gets to that Lambda, it's going to call into what's called a bootstrap method. Basically, fill in the blanks method. I don't know what to do at this point. I'm doing invoke dynamic. I've got this Lambda thing I'm looking for. Someone's got to provide it for me. And that's what Lambda Metafactory does. It's an internal class in the JVM. And it takes in, OK, I've got a comparator. This is the interface that I need to implement. I've got this target body of code. I've got a Lambda somewhere in my application. I need to stitch those two things together so that I give you a comparator object that does what your little Lambda code did. And so it does that, generates an interface that actually calls using method handles. Method handles came along with invoke dynamic. They are essentially a function pointer. So we take our function pointer that points at the Lambda body, we stuff it into a comparator implementation, and then we've got the object forever that we can use. We've got an object in hand that represents that Lambda. And there, you'll notice in the middle here, we've got a static invocation. Well, this is actually the code that was in the Lambda. So the body of our little tiny comparator implementation essentially just calls a hidden static method that was emitted into the same class. This is how we get away with not having another class file on the system. We say, OK, all we want is the body of the code. Let's just stuff it away, hide it inside the class, and then wire it up at runtime. Create the wrapper around it lazily. And then once we actually get into the Lambda body, there's what you would expect. Now we're loading our arguments, we're getting the lengths, and then doing a compare on it. So here's where our actual Lambda body lives, inside this hidden private static method. And all the state is passed into it. This is part of the magic of Lambdas versus inner classes. Rather than creating a new object every time, rather than capturing state from around it, all values that the Lambda uses are passed directly through on the stack. It means we can use a single Lambda object everywhere in the system and not have to keep reconstructing it every single time. That's pretty cool. And we don't have any extra overhead on the file system, any extra class files, and we have the lovely Lambda features that we have now. But does this optimize the way that we want? Does it actually blend and fit together? So let's take a look. So the problem here is that in order to inline code, we need to have a consistent target. It needs to be the same thing that we're calling every time. That's fairly obvious. But we also need to have a distinct path to get to that method, to call it. We need to have this method A calls method B calls method C. It is always that way. I can inline the three of them together. And now, unfortunately, what we're doing here with collection.sort is breaking one of those requirements. Collections.sort is called by who knows how many different paths in the system, many different ways that we call sort, many different lambdas that we pass into it. And as a result, the JVM usually can't see through this, except in the very trivial cases. That one sort method calls a million other methods. There's no one distinct path through it. And it kind of looks like this. So we've got all these different callers. They're each calling sort with their own lambda or their own comparator implementation. We can understand that there's a path that goes directly through this code. Caller 1 always uses lambda 1 and so on. But Hotspot today can't do anything else about this. It can't see that this sort method is being used differently in all these different places. It's trying to inline into sort, and all it sees there is hundreds, thousands of methods being called. So that's a bit of a problem. So let's actually create a little benchmark for this, and we'll try and run it and see. We'll force the JVM to do its optimization and see what happens. Here we've got our loop. We'll just iterate and time this logic a little bit. So here we go. We're just going to do the two versions, the get initials, which is the one that uses lambdas directly and calls collections.sort. The get initials manually does it by hand. It doesn't call through an existing method at the JVM level. So we avoid that choke point in the middle. OK, let's see how this does. So if we look at the version that actually uses, in this case, the streaming API, so we're calling a map method and a collect method that are already out there. They come with the JVM. They're the same map and collect that everybody uses. We can see that map and collect will inline just fine. That makes sense. Map is going to be called the same method all the time. We know what we're mapping against. But unfortunately, once we get down to actually calling the lambda within the streaming API, it can't inline. It has to do a separate call. And so this is a bit of a problem. This wonderful feature that we got, lambdas, does not optimize the way a lot of other code does, or does not optimize the way we might naturally think it should. I mean, I can see that I'm always calling sort the same way at this point in the code. Why can't the JVM? Well, this is work that's yet to be done. Let's look at our manual version. So this is the one that doesn't use the streaming API at all. It does it all by hand. So it's still using lambdas, but it's custom written for this particular application. Always going to be the same code, always going to call the same lambdas, and this actually does inline all the way through. All of those lambdas optimize the way we want them to. So I don't want you to think that lambdas are a problem as far as optimization. It's just there are some certain patterns that you use with lambdas that don't optimize quite like you would think they would. And you need to look at the lower levels to figure that out. OK, so what all have we learned today? Well, hopefully we've all learned this over the course of our careers. The JVM really is an amazing platform. These optimizations it's able to do basically pay our salaries. We're actually able to write applications that run well, that do a great amount of work with very little actual overhead. But there are places where it's not quite perfect. And it'll always be this way. There's always more optimizations that can be done. You can always wish for that sufficiently smart compiler to come along and make your bad code run better. But there's always going to be little bits and pieces that don't optimize as well as we'd like. And every feature that is introduced into a language or introduced into the JVM has a cost. There is a cost behind these that will add up over time. And you'll be a better developer if you remember that. If you know how these features work at some level, you'll write better code. You won't have to wait for the mythical smart compiler to fix your application for you. And if, like Alice, you're not afraid to go down the rabbit hole and look a little deeper, you can learn these things. They're not that difficult to follow. Hopefully this talk will help you. If you want to talk to me or ping me online, feel free to email or tweet me, and I can answer any questions you have about this stuff. But I just really wanted to get across that you can learn how to use these low-level tools, a little bit of practice, and you will be a better Java developer as a result. And that's all I have for today. Thank you.
Thanks, Charles. Actually, we have about 8 minutes for questions.
Perfect.
If anyone wants to ask, please raise your hand, and we'll give you a microphone.
Thank you for the great talk. And back to that string switch example, is it really necessary to compile it into two subsequent switch instructions? I guess it would be possible just to get rid of that synthetic variable and just do the actual payload inside the first lookup switch without adding additional table switch. Why it was done this way, don't you know?
I'm not actually sure why it was done as two switches. You are right. Like, you could just do the lookup, do the equals, and then have the logic that you were going to do at that point inline in the lookup switch. The person who actually explained to me how this is compiled and who can explain why it's done is Joe Darcy. If you ping him online, maybe we should all just, as a group, ping him and ask him why it was done as two switches, and then we can figure out the answer to that. But I'm not really sure why it was split up into two switches.
Okay, thank you.
Anyone else? Anyone? No one? Okay, you can always find Charles.
I saw one right over there.
Somewhere? Ah, okay.
Why isn't there a compatible disassembler in GDK? Why do we need to download it from some third-party site?
That's a great question. Next. I don't know the answer. I really don't know why the assembly dumping plugin is not provided along with the JVM, at least the default one. Yeah, I agree. It should be in there. But I mean, it's not too bad. You go and download this library. It's pre-compiled. You drop it into your JVM under like the JRE/server directory, I think, and then it will just pick it up. And usually that's good. Is it a license issue? Okay, so there's one answer. It's a license issue. It's like a GNU disassembler is what it's in it or something. Okay, that makes sense. So it's a thin wrapper around the GNU disassembler library, and that license-wise is not compatible shipping that with the JDK. So you have to do a little extra work to go get it.
Thank you, Charles. I have one more question.
Okay.
And the question is,
where are we?
I'm here. On the other side.
Wave your arms around.
The other side.
There we go. Okay.
Yeah. So the question is, what is the structure of, invoke dynamic caches all generated code, as I said, forever, and what is the storage technique to store it?
Oh, so after the invoke dynamic, the Lambda metafactory, after it creates the Lambda, where does that go?
Yeah, I mean, what does it mean when you say it caches it? Where?
Right. So just like the JVM knows about those strings that are in memory at any given time, it has a location that it stuffs that into. It goes into an address in memory. I would guess it's probably attached to the class data somewhere. I'm not exactly sure. That'd be my guess about where it's stored. Every one of the classes in the system has a table of information about it, methods and fields and whatnot. Inside there, it can also stuff some additional data like the lambdas.
Well, and that means when you add more dynamic code with, for example, method handles and so on, wouldn't it be too long to find if it's already stored in the cache?
Okay. So are we going to keep going after it every time? Is it going to be a lot of extra logic for invoke dynamic? Well, in this case, the invoke dynamic just bootstraps that once. It creates that object, stuffs it back in, and due to the magic of invoke dynamic at the JVM level, it actually just looks like that object was always there.
Oh, thank you.
Yeah. And for more information on that, you can check out my invoke dynamic talk from yesterday. Anything else? One in the middle here.
And for the case when we have a Lambda passed to some shared code, wouldn't be enough just to inline all the way through from the source of the Lambda to actual use of it, or it's just too bulky code and we don't want to have it in one context?
Right, so basically if you have a Lambda that's just statically defined in the application, it's only used once, it's only used in this single place, could we do it at the Java C level? Is that what you're saying?
No, I'm saying if we JIT compiling the code and we see that, well, we know the Lambda at one context, and we know that we are passing it into some code which will eventually call it, probably we want to inline all the way through.
Right. Oh yeah, sure. That would be a great way to solve it. So everywhere that you see sort being used with a Lambda, well, let's just put sort in there first, and then also the Lambda will come along with it and optimize. The problem, as I understand it, in at least Hotspot's JIT, it does the profiling and gathering of information. It figures out what methods are being called as one phase, and then it does the inlining as a separate phase. If it could profile, inline, we might do a better job at that. But by the time we've done the profiling, we've already determined it's a mess at that point. We know that this method is being called in lots of different targets. So the two phases are kind of the way that they're ordered, it doesn't work out. If we could say inline the sort method first, then do our type profiling and get the Lambda and inline the Lambda then, yes, that would optimize it. But this essentially is a specialization. It's that you would have to have the JVM say, okay, every time I see sort, let's make a custom version of it first, and then run that and gather the profile from there, figure out what Lambda is being called. Certainly something that could be done, but it hasn't been done yet.